decay. Anything that you tried, anything that you have for me, anything. Anyone, please, anything. Okay, so the models will be given to you in chapter 4. You don't have to memorize anything, but we do know P e to RT. We do know, we've seen this, and we will see this in a moment. Do you see any resemblance here? And the answer is a lot, right? This was the principle that we deposited for continuously compound interest. This is the initial number of people or fish or birds. This is the initial mass. R is like K, a rate, and T is time. It's just that they have different meanings. So this is the exponential growth. The first one is continuous compound interest. This middle one is exponential growth. And this is the exponential decay. As you see, it's the same model. However, it will be given to you. So last time we looked at, the last problem we looked at was the exponential growth. Let's take a look at the exponential decay. I'm just looking for a second. Did we talk about when the population doubles? Did I add that question? No, not last time. I'm going to add it in right now for the exponential decay. Okay, so this is on page, this is still 4.5. 4.5. Let's start with page 530. Okay, let's look at problem 19. Let's read the problem. Use the exponential decay model for carbon-14. This is the radioactive substance. The name is not important for us. And here's the exponential decay model. It's not given as A of t, so be careful. It's A of t equals A0 e to negative 0.30 t. So that's the model, and then let's see what they want us to do. They say that prehistoric cave paintings were discovered in a cave in France. The paint contained, when they were discovered, they contained 15% of the original carbon-14. So 15% of the original amount or mass. So they discovered the paintings. They measured the amount of carbon-14, and they said, okay, we don't know what the original was, how much it was, but we can tell that right now what is left on these paintings from the radioactive substance that diminished its mass in time is only 15% of the original amount. Question. Estimate the age of the paintings. The key word is this. And then this. When I'm told I have 15%, or I'm telling you, you have $100 in your pocket, and I'm telling you I have 15% of what you have. How much do I have in my pocket? $15. Is that clear? Very good. So now we know, so remember what these letters represent one more time. This is the initial amount. Initial mass, initial or original, or the starting point. E is a number. No worries about it. The rate is another number. Constant. T is the time. This is what we would like to determine. And this is the mass today, now, or at any point in time. So we are told that right now, the amount of carbon-14 on the paintings is 15% of what it was originally. So, what do you recommend we write? Obviously something in here, something that is connected to this equation. The right-hand side must be A0 times e to negative 0.00121 t, because I don't have the original, I'm after the time, and these two are constants. So this I don't have. This is a number, and I'm asked to find t. So this is my variable, t. Now the question is, what do I have on the other side? That's the key. So the original was A0. Today we have 15% of it. So what do I write? Exactly. So it's 0.15 times A0. The of means multiplication. 15% means 0.15 of the original. That's it. Great. Okay. So now I'm asking myself, what is this? What type of equation is it? And the answer is it absolute value? Is it radical? Is it logarithmic? Is it linear? Is it quadratic? Which one? It does not have log in it. It doesn't have ln. Nope. It is exponential. Because this is a constant, we're not going to need it. The variable is at the exponent level, and there are no other variables, because I'm going to divide both sides by A0 anyway. So now the equation is exponential. We have 0.15 equals e to negative 0.0000121 t. And now I'm asking myself, how do I solve this equation? That's the key next. That's the next step. And I know I would like to be able to apply a mechanism that brings that power down so I can solve. And there is only one function that will do that. Which function will do that? Or log. So the reason why I use ln is it's easier to write, but it doesn't matter. You can apply common log, log, to both sides. You will get the same answer. But just be careful that to apply the same function to both sides. If you apply here log, you have to apply here log. If you apply natural log here, then you apply natural log to the other side. So then you have natural log of 0.15. We bring the power in front. And I should write multiplied by what? Natural log e. But how much is natural log e? 1. So remember, natural log e is 1. What about log in base a of a? How much is that? A raised to which power is a? So log in any base of the base will always be 1. One more little property, log in any base of 1. Don't say anything, just convert it into an exponential. A raised to which power is 1? 0, indeed. A raised to 0 is 1. Very good. So now, in order to determine t, do not get impressed or concerned or worried about this. This is just a number. I know it looks fantastic. Natural log in front of it is just a number. This is just a number. We are solving for t. So t equals natural log of 0.15 over negative 0.00121. So let's use the graphing calculator. We can't determine this without it. I had all the time in the world because my students are taking a test, and I had all the time in the world to prepare this, and I didn't. Sorry about that. So we have a natural log, 0.15, close, divided by, in parentheses, negative 0.30, 1, 2, 1. Close the parenthesis and press enter. So we got 15,679 years approximately. That's how old they are.
Where did you get the LN? Like, how did you get that?
The key LN,
Yeah, I don't see it.
it's in the left column.
Never mind.
That's okay.
Thank you.
No problem. Okay. Any questions? Any questions? Okay, let's look at another before we continue with chapter 5. Let's look at another exponential decay or exponential growth. Any questions? Any questions? Any questions for me? 86 on page 538. Are we okay? Are we all set? Yes? All set? Okay, perfect. So according to the U.S. Bureau of the Census, in 2000, there were 35.3 million residents of Hispanic origin living in the United States. By 2010, so this was into year 2000. In 2010, the number had increased to 50.5 million. The exponential growth model or function is A of t equals 35.3 times e raised to kt. Describes the U.S. Hispanic population A in millions t years after 2000. So if t is number of years after 2000, it means that, t equals what for 2000? Say it again.
10. That'll be 0.
0, right?
Yeah.
Yes. So t is the number of years after 2000. Therefore, t equals 0 for 2000. Find k. So that's the first question. Like we looked at the similar problem last time, we said that this is an ordered pair and this is an ordered pair. Can anyone give us those two ordered pairs? And then we'll know what to do next.
0 and 35.3.
Very good. Which is already taken care of because they replaced A0 by 35.3. And what about the other ordered pair?
10.
Thank you very much. That's it. So then, this was already taken care of. Now I would like to plug this point in the model. Can anyone tell us how to plug in the point 10, 50.5 in the model? Say it again.
50.5
Correct. A of t, 50.5
equals 35.3
times e to k
times 10.
times 10. So this point says when t is 10, a of 10, say it again.
It has to be 10K, not 50.
Oh, of course. Thank you. When t is 10, then a of 10 is 50. A of 10 is 50 when t is 10. Okay, good. How many variables we have in this, and what type of equation is it? Very good, because the variable is at the exponent level. So I have to clean it up first. How do I clean it up? I will. I can't, it's not ready yet. Yes, I need to get rid of this. So we divide both sides by 35.3. 50.5, 35.3 equals e to 10k. Do not bother with dividing, per se. Just write it as a fraction. Now, I would like to apply a mechanism or an operator, if you want, or a function to both sides that allows us to bring 10K in front, but it has to be applied to both sides. What will I write? Yes, either ln or log. It's up to you. ln is easier to write. Equals 10K. I should write multiply by natural log E. However, I don't. Why? Because natural log E is? Very good, awesome. So then K equals natural log of 50 over 5 over 35.3. Remember, this is not log of the top over log of the bottom. It's log of a ratio divided by 10. If you have the number for me, please give it to me. Don't torture me. If not, I will calculate it. So, we have it. Please. Yes? How much? 3.5, and what is the next digit?
8.
And the last one after that?
9.
Okay. We agree? We 0.0359? Okay, very good. I got one nod. That's good enough for me. So I have the model now. Agreed? Okay, here's the model. A of t equals 35.3 e to 0.0359 t. T is like x, a of t is like f of x. So we have the model or the function. Part B, use the resulting model to project the Hispanic resident population in the year 2015. Part B, in 2015. What will I have to do to find the projected, or what it was, since that was already 3 years ago. Awesome, thank you. So 35.3 times e to 0.0359 times 15. And if you have the answer, please give it to me. If I need to show any calculations, please say so. How much was it? Do we have the number? Okay. So then we have 35.3 multiplied by e raised to 0.0359 multiplied by 15, close the parenthesis. I got 60.5. Measurement unit, please. Thank you. Next question, part C. In which year will the Hispanic resident population reach 70 million? What do I have to do next? Correct. So what do I write? Here's the model. How do I write it?
So on the left side is going to be 70.
Very good.
And then 35.3 times e to 0.0359.
Very good. We want to determine when, if the model is still correct, the population will be 70 million. Very good. How do I solve this exponential equation? I have to clean it up. Very good. 70 over 35.3 equals e to 0.0359 t. Now? Yes, of course. So ln 70 35.3 equals 0.0359 t, and t equals natural log 70 over 35.3 over 0.0359. I'll put in the graphing calculator, and that's natural log 70 divided by 35.3, close the parenthesis, and divide everything by 0.0359. So approximately 19 years. And according to the model, which year will that be?
2019.
Very good. Now I would like to add a question here. Part D. First of all, let me ask you if you have any questions. Is this okay? Are we okay? Yes? Any questions? D. When will the population, which is the original, the initial, when will it double? What was the original?
35.3.
Perfect. And I would like to determine how many years it needs for that original to double. What do I have to write? Any suggestions? How do I solve this?
Would be 70.6 equals, and then you do the
Yes, so we are saying 2 times 35.3 equals 35.3 times e to 0.0359 t. Why do you think I did not want to multiply? Because I still need to simplify it. I still need to divide both sides by it. Is it wrong to multiply and say 70.6? No, you still have to divide by 35.3. So this is natural log 2 equals 0.0359 t. So t equals natural log 2 over 0.0359. And we will find out it's possibly close to 2019, right?
Yeah.
So let's see what we get.
19.307.
So approximately 19 years. Because 70 or 70.6 is pretty close. So in 2019, it's supposed to double. Okay. I would like to look at one more exponential decay. So let's say on page 529, let's look at problem 15. James finished?
Yep.
Everything?
Yep.
I will see you on Tuesday, not Thursday. Okay, so we're told that an artifact originally had 16 grams of carbon-14 again present. The decay model, of course, A of t equals 16 e to negative 0.30121 t, describes the amount of carbon-14 present after t years. Use this model to solve exercises 15 and 16. So here's 15. How many grams of carbon-14 will be present 5,715 years? What do we have to do? What is the amount 5,715 years later? That's it. So I'll put it in the graphing calculator right away. And I have 16 16 E in parentheses negative 0.30121 multiplied by 5715. So initially there were 16 grams. After 5,715 years, 8.013 grams. Why does it take so long for 16 to get to 8? Because look at the rate. The rate is so small, is 0.0121%. So it diminishes its mass at a very, very slow rate. It's a radioactive substance that diminishes its mass at a very, very slow rate. Okay. Any questions? Okay, let's look at 17 and talk about half-life. Would you say that 16 grams approximately gets in half in 5,715 years? This is very close to 8. So we started with 16 grams and now it's down to 8 after 5,715 years. This is what we call the half-life, the time needed for any mass of a certain radioactive substance. The number differs depending on the substance. So for this one, it takes way more than 5,000, almost close to 6,000 years to get from 16 to half. But there are other substances that, like for example this one in problem 17, the half-life of the radioactive element Krypton 91. Again, the names are not important. We're not going to do anything, but at least we know the difference. So carbon 14 needs roughly 6,000 years to decay to half of it. In other words, the half-life is 5,700 a year. So this is normally denoted by lowercase h. For this one, however, for Krypton 91, the half-life of the radioactive element is 10 seconds. So if I have, and we are told that there are 16 grams present, so A0, the original amount is 16 grams. Can you please tell me what happens in 10 seconds? 10 seconds later, the amount for 10 seconds becomes 8. Then 10 more seconds later, A of 20 seconds, it becomes 4. 10 seconds later, A of 30, that will be 2. And 10 seconds later, A of 40 will be, you barely count and it disappears, right? You barely count to 10 and it disappears. Half of it goes away. And 10 more seconds later, A of 50 is 0.5 over gram.
Is it gonna sound like a stupid question?
No, it doesn't exist. Yes, go ahead.
How did you get it to go from 16 to 8?
So we are told that the half-life is 10.
Oh, so half of it. Okay.
Exactly. The
Okay.
half-life is 10 seconds. So if we have, well, we shouldn't because it's a radioactive substance, so we have to be careful. But assuming in a lab we have 16 grams, 10 seconds later, if we expose it, if we don't expose it to air, it's a different story. But we expose it to air in 10 seconds, 8 of those grams dissipate in thin air.
Okay.
And in 10 more seconds, 4 more grams dissipate in thin air, and so on and so forth.
Okay.
Does it make sense?
Yes.
Okay, perfect.
Thank you.
So let's, do you think we need other examples of this? Are we okay with that? Okay. Well, let's start chapter 5. Chapter 5, there are 3 sections in chapter 5. As I mentioned, I think you will remember most of it. About 15%, you shouldn't because it's new. So chapter 5. In Chapter 5, we will talk about systems. Systems of linear and nonlinear equations and also inequalities. It's a big title. Okay, let's start with 5.1. Systems of two linear equations in two variables. Nothing new in this section. However, we'll start from scratch. The two methods we are going to look at are substitution and elimination, also called the adding method. Whatever you want to call it, it's not important. Okay, so let's start by looking at a couple of examples with substitution. So let's say problem 14 on page 555. System of 2x plus 5y equals 1 and negative x plus 6y equals 8. Is this a system of two linear equations? Yes. So what can happen here? There are three possibilities. Since this is what? If you want to graph 2x plus 5y equals 1, what will you graph? Will you graph a parabola? Will you graph a rational function? Will you graph a line? Of course, a line. Thank you. So they are both lines. So two lines can meet in one point. That's the first option. We call this unique solution or one solution. The system can consist of two parallel lines. How many points do two parallel lines meet?
Never.
Never. No solutions. And the last one, here's the third possibility. Here is one line, and here's the other. In how many ordered pairs do these two lines meet? Indeed, infinite many solutions. This system is called inconsistent system because it has no solutions. These two have solutions, so they are called consistent. They have solutions. They're consistent. Okay, so now let's analyze the system that we are given to solve using substitution. So I go back to the system. I look at the coefficient of x here. It's 2. Do I want to solve for x? No, because if I move 5x, I will have the fraction divided by 2. Do I want to solve this one for y? No, because I moved 2x, but I have a fraction divided by 5, right? Do I want to solve for this y? No, for the same reason. This is the only one that I will ever think of solving for. If the coefficient is 1 or -1, if it's any other number, I would not consider using substitution unless I can simplify somehow and still get back to 1 or -1. So I will solve this equation for x. So I have negative x equals negative 6y plus 8. And of course, I will multiply both sides by -1. So then we have x equals 6y minus 8. This is good. However, now I have to go back to the first equation and replace this x by what I just found out, meaning that x equals 6y minus 8. So then the first equation becomes 2, parentheses 6y minus 8 plus 5y equals 1. So what did just happen? Really nothing much. I manipulated algebraically one equation by solving it for x and replacing the result in the other one. Not much. Nothing impressive. However, here's the accomplishment now. I managed to get an equation with only one variable, and this I know how to solve. And it's a linear equation. All I have to do is distribute, move terms around, and then just get the solution. So 12y minus 16 plus 5y equals 1. Combine like terms to get 17y. Move 16 to the other side to get 17. And divide by 17 to get 1. Is this good? Yes, it's good, but it's not good enough. How come? Well, I have to go back and replace y in the equation with x. So I can find x. So can anyone give us x when y is 1? Negative 2. It appears that this system has the solution. Which solution? Right. It comes with a big question mark. I have no idea. I have to go back and check. I don't know if it works. And I don't need anyone to tell me whether I have an error or not. I'll go back to the original problem and check. I'm checking negative 2, 1, negative 2, 1. 2 times negative 2 is negative 4, plus 5 is 1. Check. Negative 1 times negative 2, oops, sorry. Negative 1 times negative 2 is 2, plus 6 is 8. Check. Therefore, it must the solution must check in both. You have to check both. Then I will say yes. I checked in both. Both solutions, both equations are true when I replace x by negative 2 and y by 1. So this must be the solution, and there is no other. This is the method of substitution. Let me know if we need another. We'll choose another. Of course. Okay, still on page 555, let's look at 18. Here's the system. Y equals negative 1/2 x plus 2, and y equals 3/4 x plus 7. The same requirement. Use substitution to solve the system. There is no effort here, really, because y is already, one equation is already solved for y. I'm going to replace the y in the second equation by what y from the first equation equals to. This is already done for us. I didn't have to solve. It was already solved. So then this y is this, but it's the same y. So on the left-hand side, I have negative 1/2 x plus 2 equals 3/4 x plus 7. They must be equal to each other because there is only one y. Okay, so then I see that this is what type of equation? We have so many. Quadratic, absolute value, logarithmic, exponential, quadratic in form, polynomial, radical. So it's what type?
Linear.
Correct. Very good. There is no x in the denominator, so it's definitely linear. Perfect. So I recommend moving to and then eliminating fractions. Negative 1/2 x equals 3/4 x plus 5. And then multiply both sides by something to do the magic that removes all fractions. The least common denominator, and that would be perfect. So negative 1/2 times 4. Perfect, awesome. Negative 2x. 3/4 times 4/1.
4. Now 3.
Very good. Plus 5 times 4. So remember, we have to multiply everything. So I move 3x, so I have negative 5x equals 20, so therefore x equals negative 4. Is this good? Good, but not good enough. Have to go back. I go back with negative 4. Negative 1/2 times negative 4/2. Negative 1 over 2 times negative 4 over 1, I meant to say. Simplify. 2. So negative 2 plus 2. It was positive, forgive me. It was positive. Negative times negative. So positive, yes, 4. So y equals 4. We'll check in a minute. We'll know whether we have an error in a blink. So it appears that this system has the solution. We don't know yet, but it appears that it has the solution. Awesome. I don't know. I don't trust it. I'll have to go back. I'm going to write the system here one more time. So y equals negative 1/2 x plus 2, and y equals 3/4 x plus 7. Okay. So I'm checking negative 4 and 4. Negative 4, 4. Negative 4, 4. So negative 1/2 times negative 2 is 2 plus 2 is 4. Check. 3 over 4 times negative 4 over 1 is negative 3. Negative 3 plus 4 is 7. Check. And then I will say, yes, indeed. So this is the method of substitution. Any questions? I'm sure you remember at least part of it. Yes? Okay, so let's move on to elimination. We're going to have, this will recur in the next sections anyway. Okay, so let's take a look at, let's say 24. Same page, 5, 5, 5. 2x minus 7y equals 2, and 3x plus y equals negative 20. Now, if you ask me which method I prefer, I will always say elimination. If you ask me which of the two methods will always work, I will say elimination. Which of the two methods I would say work, but it will be more difficult to work with fractions is substitution. So even substitution will work, but it will be more work to do. Okay. So I want to eliminate one of the variables, and I'm looking at 2 and 3. The multiple, the least common multiple is 6. So I will have to multiply this by 3 and this by negative 2 to get a positive 6x and to get a negative 6x, in case we eliminate x. Now let's also think about eliminating y. If we eliminate y, it is easier because I only need to multiply the second equation by 7 to eliminate. So I prefer that. I don't want to multiply both equations. Not because I'm lazy, but because I would like to use the easiest route. So I will copy 2x minus 7y equals 2 and multiply each and every term, both sides, by 7. 21x plus 7y equals negative 140. The adding or the elimination is very clear now. When I add term by term, y, terms with y will go away. And that was the target. Now I have to add 21 to 2, so I get 23x. And then here I get negative 138. Now what happens is, exactly, so x equals negative 6. Yes. So is this good? Yes, it's awesome, but it's not good enough. Have to go back to any of the equations. It doesn't matter which one you pick, but I have to go back to one or the other to determine y. So I have negative 12 minus 7y equals 2. I will move negative 12 to the other side because it's linear, and I will divide both sides by negative 7, so I get x, not x, but y equals negative 2. So then, the ordered pair is? Very good. Do you trust it? I don't. I don't know. It's very possible, very easy to make a mistake. Please go back both equations and check. So negative 6, negative 2. Negative 6, negative 2, negative 6, negative 2. So 2 times negative 6, negative 12, plus 14. Negative 7 times negative 2 is positive 14. 2, check. Negative 18 plus negative 2, negative 20, check. Yes. Indeed, negative 6 comma negative 2 is the correct answer. Any questions? What will happen if we get, let's say we solve and we get 5 equals 3. When I manipulate the equations, I get 5 equals 3, and I don't have any x, I don't have any y. Which of those 3 cases is this?
No solution.
No solutions. No solutions. What if I don't get x, I don't get y, but I get 10 equals 10? Which of these 3 cases is it? Exactly. Exactly. Any questions? Do we need another elimination? We're going to use it again in the next 3 minutes. Anyway, in section 5.4, in which we are going to discuss the same thing, but nonlinear systems. So 5.4, nonlinear systems. We call them 2 by 2 like the other ones. Two equations, 2 variables. Okay, so let's start with elimination, with substitution and then elimination. For example, let's look at 8, page 587. X squared plus y squared equals 5, and 3x minus y equals 5. Okay. Can you say that this is a linear system of equations? The answer is no. This happens to be linear, but this is not linear. Does anyone remember from chapter 2? Yes, chapter 2 what this was?
That's a circle.
A circle, very good. With a center at the origin. And what is the radius? Square root of 5. Very good. So this is not linear, this is linear. Good. So I have no way of using elimination here. So I should have not spoken, I was talking about linear systems. But here I have no way of using substitution. Elimination. Why? Because I don't have the same variables. So elimination here does not work for this particular nonlinear system. So my only chance is to substitute. I will not substitute for this because it has 3 in front. I will substitute for this because it has positive or negative 1. So I'll solve for y. Negative y equals negative 3x plus 5. And of course, we divide or multiply both sides by negative 1. So I'm fine with this. Good, but not good enough, of course. I have to go back to the first equation. Replace y by 3x minus 5 in the first equation and square it. So the first equation is this now. And I know you remember our first handout in August. It dealt with this. And that appeared almost in every class. And that's why I didn't want to talk about it anymore. So how many terms will you give me when you square a binomial? Exactly. Very good. So we have x squared plus, very good, awesome, 9x squared minus all multiply first by 5, right? It's easier. 2 times 5 is 10 times 3.
30.
Very good. Plus,
25.
very good. It's quadratic. I have to subtract and set it equal to 0. Let's combine like terms now. 10x squared minus 30x You know exactly what we need to do. If you don't remember much from this class, but you remember factor and simplify, you will be comfortable with algebra. What would you recommend? Divide everything by? I would not work with these numbers. So yes. So x squared minus 3x plus 2 equals 0. Awesome, thank you. Good. Is this good? Yes, it's awesome, but not good enough. Why? Because we only determined x. So now I have to go back here with this and later on with this. So when x is 2, how much is y? 1. So 2 comma 1. When x is 1, how much is y? Negative 2. So the ordered pair is 1 comma negative 2. Please remember to go back and check. Can I skip that part? We should never skip that part. Can I skip that part and you check? Yes? Okay. Should we look at another substitution? Should we look at another substitution with a nonlinear, or can we look at elimination? Elimination? Okay. So let's take a look at let's take a look at 22. If you want to choose, please feel free. 3x squared minus 2y squared equals negative 5. 2x squared minus y squared equals negative 2. Okay. Which of these two variables, x squared and y squared, you consider eliminating? Of course, because it will be the easiest thing to do to just multiply one equation, which is the second one, by what? By? If I multiply it by 2, it's not going to be good enough, because negative 2y squared minus 2y squared is not 0. Exactly. So I copy the first equation as 3x squared minus 2y squared equals negative 5. And I copy the second one as negative 4x squared plus 2y squared equals 4. Now I know that I can easily get rid of what I wanted to get rid of. One is negative 2y squared. One term is negative 2y squared. The other one is positive 2y squared. That's why they go away. So now perform the operations. Negative x squared equals negative 1. I like this. But what do I need to do next? Divide both sides by? Of course. Or multiply. It doesn't matter. It's the same thing. So then I have x squared equals 1. I know that this is quadratic. X squared equals 1, quadratic. But I would like to use the exact method that will give us a solution in a blink. Which of the 4 methods is applicable here? We have factoring, we have taking square roots, we have completing the square. I'm sorry? Taking square roots. Very good. Awesome. So x equals? Never? Thank you. That's why I said quadratic. 2 solutions. Good. Is this good? Yes, but not good enough. So I have to go back to the first equation or the second, it doesn't matter. And I will replace x squared by 1. So I have 3 minus 2y squared equals negative 5. What next?
Subtract 3.
Correct. 2y squared equals negative 8.
Divided by -2.
Very good. So I have y squared equals 4. I like it.
Take the square root.
Awesome. How many solutions do I get? Right. Now I have to list the solutions. When x is 1, how many options we have for y? When x is negative 1, how many options we have for y? 2. So that's why we have to write 4 different solutions. Can anyone give us all those 4 solutions, please?
1, 2,
Very good. 1, comma 2.
1, comma -2,
Very good.
-1, comma 2,
Very good.
and a -1, comma -2.
Perfect. Awesome. Well done.